In this section, we're going to be going over tree diagrams. So first, before we get into how to create tree diagrams, let's go over something that's really important in probability and statistics, and that is the counting principle. So the counting principle tells us how many different outcomes we have in an experiment without having to list them all out. So it states that if the first experiment can be performed in m distinct ways, and a second experiment can be performed in n distinct ways, then the two experiments in that order can be performed m times n distinct ways. So what we're going to be doing here is we're going to be multiplying. So for example, how many possible outcomes are there when a coin is tossed and then a die is rolled? So we know that there are two possible outcomes when we toss a coin, and there are six possible outcomes for rolling a die. So that means the two experiments together are going to have 2 times 6, which is 12 possible outcomes. Okay, let's see another example before we get into tree diagrams. So if two letters are selected at random from the English alphabet, we want to determine the number of possible outcomes if the letters are selected with replacement and without replacement. So the first one, with replacement, we have 26 options for the first letter, and we're choosing two letters. So we're taking the letter out and essentially putting it back in. So that means we have 26 options again for the second letter. So the total number of possible outcomes is 26 times 26, which gives us 676 possible outcomes. Okay, for the next one, we have the same question except without replacement. So that means we're going to choose a letter, and then we're not going to put it back, and then we're going to choose another letter. So we have 26 options for the first one, but since we don't put it back in, that means we only have 25 remaining options in the alphabet. So it's 26 times 25, which is going to give us 650 possible outcomes. Okay, so now let's move on to tree diagrams. So using the counting principle, we can determine how many possible outcomes an experiment can have without actually listing them out. Now what we're going to do is we will actually list out all of the outcomes using a tree diagram. So first, let's do some definitions here. So a list of all possible outcomes in an experiment is called the sample space. So sample space is all possible outcomes, and each individual outcome in the sample space is called a sample point. So let's do that same example from before. Let's create a tree diagram illustrating the possible outcomes when a coin is tossed and a die is rolled. And let's see how we set this up. So we said we are tossing the coin first. So let's have a column for possible outcomes from a coin. And we know that these possible outcomes are going to be a heads or a tails. And let's list the possible outcomes for rolling a die. And these possible outcomes are going to be 1, 2, 3, 4, 5, and 6. So what we're going to do is we're going to give each one of these that possible outcome. So we're going to have 1, 2, 3, 4, 5, and 6. And then for tails, we're going to have the same thing. So what this means is we're going to either flip a heads and then roll a 1. We're going to flip a heads and then roll a 2, heads and 3, heads and 4, heads and 5, or heads and 6. Or we can toss a tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, and tails and 6. So this is a tree diagram, and called that because of these branches that are coming off. And this actually tells us all of the possible outcomes, which is going to be the sample space. So let's go ahead and list this sample space over here on the right. So first, all we have to do is essentially follow these branches. We can either have a heads in a 1, a heads in a 2, a heads in a 3, heads in a 4, heads in a 5, heads in a 6, or we can have a tails in a 1, tails in a 2, tails 3, tails 4, tails 5, or tails 6. Okay, so that is the tree diagram for these experiments, and that is the sample space or all the possible outcomes listed out. Let's do another example. A radio station has 2 tickets to give away to a Blake Shelton concert. It held a contest and narrowed the possible recipients down to 4 people: Christine, Mike, Larry, and Phyllis. The names of 2 of these 4 people will be selected at random from a hat, and the 2 people selected will be awarded the tickets. So let's use the counting principle to determine the number of sample points in the sample space. Okay, so for the first one, we have 4 total people. We have Christine, Mike, Larry, and Phyllis. So that means we have 4 options for the first one, and we're going to multiply that by the number of options for the second one. Since we already took one out, we already took a name out of the hat, that means we have 3 options left for the second person. So 4 times 3, that gives us a total of 12. So it's 12 sample points in the sample space. Okay, so now let's go ahead and construct a tree diagram, and we're going to list the sample space out. So for the first column here, we're going to have we'll say the first selection. It's going to be the first name drawn. So we have 4 options. We either have Christine, Mike, Larry, or Phyllis. So I'm just going to abbreviate. I'm going to say C, M, L, or P. And then we have the second selection. So the second selection here is going to be a little bit trickier than the first one that we did before. So for the first one, if we choose Christine, then the only available options from that are going to be Mike, Larry, or Phyllis. If we choose Mike, the only options available are going to be Christine, Larry, Phyllis. If we choose Larry, then it's going to be Christine, Mike, Phyllis. And if we choose Phyllis, it's going to be Christine, Mike, or Larry. Okay, so we're going to draw arrows to them. So that's Christine to Mike, Christine, Larry, Christine, Phyllis, Mike, Christine, or Mike, Larry, Mike, Phyllis, Larry, Christine, Larry, Mike, Larry, Phyllis, Phyllis, Christine, Phyllis, Mike, or Phyllis, Larry. And I'm going to go ahead right now and just write out that whole entire sample space. It's exactly what I just said. So these are all of the possible outcomes from this ticket giveaway. Okay, let's answer a question now based on this sample space. So let's determine the probability that Christine is selected. So for the probability that Christine is selected, it's going to be the number of times she was selected divided by the total number of outcomes in the sample space. So first, we know that there are, if we go ahead and count them up, and we also can use the counting principle, there's 12 outcomes in the sample space. So we know the denominator is going to be 12. And now all we have to do is count up how many times she was selected. That's going to be 1, 2, 3, 4, 5, and 6. We just count all of the sample points that have a C in them. So that's going to be 6 out of 12, which simplifies to 1/2. Okay, and now for the next one, we want to determine the probability that Christine is selected and then Mike is selected. So what we are going to be looking for is in the sample space is a CM and how many times that happens. And we go up to our sample space. There's only once where we see Christine and then Mike. So notice that MC does not work because that is Mike and then Christine. That is different. So this only happens once. So this is going to be 1 out of the total number in the sample space, which once again is 12. So that's going to be a probability of 1/12. Okay, for another example. So at Finley's restaurant, each lunch special consists of a sandwich, a salad, and a beverage. The sandwich choices are roast beef, ham, or turkey. The salad choices are macaroni or potato. And the beverage choices are coffee or soda. So let's use the counting principle to determine the number of different lunch specials offered by this restaurant. So we have 3 sandwich choices, we have 2 salad choices, and then we have 2 beverage choices. So the counting principle says we multiply them together. So that's going to be 3 times 2 times 2, which ends up giving us 12 possible different lunch specials, different combinations for those lunch specials. So let's go ahead and create a tree diagram. So for this one, let's say we have sandwich first. So for the sandwich column, and I'm going to abbreviate here, we had roast beef, ham, and turkey. I'm going to use an R for roast beef, an R for roast beef, an H for ham, and a T for turkey. So these options are going to be R, H, T, and then the next thing is a salad, and the options we had for salad were macaroni or potato, so I'm going to use an M and a P. And for a salad, that means each sandwich option gets both of those salad options. So it's going to be M and P for roast beef, M and P for ham, and M and P for turkey. And we can give each one of those, connect them with the line, with the little branches. And the next thing is the beverage, the last thing. And the beverage options were either a coffee, which I'm going to use a C, or a soda, which I'm going to use an S. And then each one of those salad options is going to get that beverage option. So it's going to be CS coming from the first macaroni, CS coming from the first potato, and now for the next one we have CS from this macaroni, CS from the next potato, CS for the last macaroni, and CS for the last potato. So this is going to give us our whole entire sample space. So let's go ahead and list it out. So now we're just going to follow each branch. So first follow the first branch. That's going to give us the option roast beef, macaroni, or coffee. And then we have roast beef, macaroni, soda for the next one. And then we have roast beef, potato, coffee, roast beef, potato, soda. And that takes care of the first part with the sandwich being roast beef. Now let's look at the next part with the sandwich being ham. That's going to be ham, macaroni, coffee, ham, macaroni, soda, ham, potato, coffee, ham, potato, soda. That takes care of ham. Now for the last one is going to be turkey. So turkey, macaroni, coffee, turkey, macaroni, soda, turkey, potato, coffee, turkey, potato, soda. Okay, so all we have to do is follow each branch and just name exactly what, which in this case sandwich, salad, and beverage we are at. Okay, let's go ahead and answer these probability questions. For the first one, if a customer randomly selects one of the lunch specials, determine the probability that the roast beef sandwich and soda are selected. So we're looking at the probability for R and S. We're going to go back up to our sample space and see how many options have an R and an S in it. So we have one here, R and S here, and that is it. So there are two possible options that have roast beef and a soda. So that's going to be 2 in the numerator divided by the total number of objects, the total number of outcomes in the sample space, which you can count them up or go back up to the counting principle. Either way, it is 12. So this is 2 over 12, which is simplifies to 1 over 6. A common factor of 2 gets canceled. So the probability of that is 1/6. Okay, next one we have if a customer randomly selects one of the lunch specials, determine the probability that neither macaroni salad nor coffee is selected. So we have to go up to our sample space and see which one of these outcomes, which one of these sample points doesn't have macaroni salad and it does not have coffee. So the fourth one does not contain macaroni salad or coffee, and the this one, the HPS, does not contain macaroni salad or coffee, and then it looks like the last one does not contain macaroni salad or coffee. So that's 3 of them total. So that means the probability that it's neither macaroni salad nor coffee is 3 divided by the total number of possible outcomes, which is 12 again. And this is going to end up simplifying, divide by 3 in the numerator and denominator. It simplifies to 1/4. Okay, so just a few more here. So 2 balls are selected with replacement. So with replacement, like we saw earlier, means we're taking it out and then we're putting it back in and then doing it again. So 2 balls are selected with replacement from a bag that contains 1 red, 1 blue, 1 green, and 1 orange ball. Let's use the counting principle to determine the number of sample points in the sample space. So for the total number of possible outcomes, when we pull out the first ball, we have 4 options. We either pick out a red one, a blue one, a green one, or an orange one. That's 4 options. And then we put it back in, and then we do it again. So since we're putting it back, that means we're also going to have 4 options for the second one. So 4 times 4, we get 16 possible outcomes, which means 16 sample points in the sample space. And for the next one, let's go ahead and construct a tree diagram. So first we are going to have our first selection, and that means we can choose a red, blue, green, or orange. I'm just going to abbreviate and use the first letters once again. So that means we can choose a red, blue, green, or orange. And then we put that ball back because it was with replacement, and then we choose our second one. So we have our second selection, and that means we're actually going to have 4 options once again. So for each one of these, we're going to have the same 4 options. We're going to have red, blue, green, orange, red, blue, green, orange, red, blue, green, orange, and red, blue, green, orange. And then we're going to connect these all with lines. And then we're going to go ahead and list off our sample space. So the sample space, either we can choose a red and a red, red and a blue, red and a green, red and an orange, or blue and a red, blue and a blue, blue and a green, blue and an orange, or green red, green, blue, green, 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 orange. And then lastly, orange, red, orange, blue, orange, green, orange, orange. So those are all of our possible outcomes for these experiments. And let's go ahead and take a look at these questions. Let's determine the probability that the red ball is selected twice. So we are looking up here for the probability of a red and a red. So the only time we see a red and a red, an R and an R is the first one. So that's going to be 1. And that's going to be in the numerator, divided by the total number of possible outcomes. So once again, we can go ahead and count these up, or we can look at our counting principle. From the first part, there's 16 possible outcomes, so 1 out of 16. So the probability of rolling 2 reds in a row is 1 over 16. And next we have determine the probability that neither ball selected is orange. So now we are looking here in our sample space to see when there's no oranges, no O's. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And that looks like it's it. So there are 9 possible times when we don't get an orange, divided by 16 possible outcomes. So that probability is going to be 9 over 16. And for the last one here, we want to determine the probability that the orange ball is selected at least once. So for at least one orange, that means we're either going to have one orange or they're going to both be orange. So let's go count. So for at least one orange, here's one orange, here's an orange, here's an orange, and then here are all of the other ones. So counting that up, that's 1, 2, 3, 4, 5, 6, 7. So that is 7 possible times that we have at least one orange, divided by 16 possible outcomes. So that probability is 7 over 16. And for the last thing, we have the probability of an event occurring at least once. So the probability of an event happening at least once, there's actually a shortcut to it. Sometimes it'll be a shortcut. The probability of an event happening at least once is 1 minus the probability that the event does not happen. Okay, so try to remember this formula. It comes in handy. So let's redo that previous question that we just did using this formula. So the probability that an orange ball is selected at least once. So based on this formula, this is going to be 1 minus the probability that neither are orange. So going back up here and counting how many don't have orange in them, we could just recognize that we actually calculated this already in question D. The probability that neither of them were orange was 9 over 16. So this is going to be 1 minus 9 over 16. And we have to remember how to get common denominators here. 1 can be rewritten as 16 over 16 to get a common denominator. Now all we have to do is subtract the numerators and we get 7 over 16. So this one probably wasn't easier to do it this way because we had the sample space listed out for us, but it is definitely a handy little formula for us. So try to remember that one. Okay, so that is it for this section.